This is Larry Moore. I'd like to welcome you back to our biological wastewater treatment training series. Today, our fifth presentation will be on activated sludge process modifications. There are a number of different types of activated sludge processes. We want to look at some of those today, and then we'll look at more of those in the next training session. All right, let's talk a little bit about, again, the components of activated sludge. Influent pretreatment, again, that's the preliminary treatment part of the process where we're removing large objects like rags and sticks and bricks and other things, and removing the grit from the wastewater, and that protects the activated sludge process. Then we go into the aeration basin or biological reactor, and that's where biological metabolism is taking place, and sometimes we focus too much on the reactor. But at any rate, when it comes out of the reactor, the influent flow and return activated sludge flow moves on to the secondary clarifier. And that's where we settle the biomass to produce a good quality effluent. And this is where we generally have problems in activated sludge. If there are problems, it comes with poor settlability of the biomass. And so secondary clarification is extremely important. You got to be able to separate the biomass from the good quality effluent. And it's somewhat of a challenge because, again, the specific gravity of biomass is about 1.05, and we know the specific gravity of water is 1. So that's not a big difference. But again, if everything's working well, the activated sludge will settle and will produce a good quality effluent. Then we take the sludge out of the bottom of the clarifier. Most of it gets returned back to the activated sludge reactor, and that's to allow us to maintain a good biosolids inventory. And then some of it will be wasted from the process, and the waste activated sludge, as I mentioned before, is how we primarily control the activated sludge process. What we see here is just some of the different process modifications that are used, and there are several others as well. These are some of the more common ones, and we'll be looking at the first 5 of these or so today and getting you more familiar with them. High rate activated sludge process is not used very often in municipal wastewater treatment because we don't produce an outstanding settling sludge, and we don't produce outstanding effluent quality. So we might say, why do we even talk about high rate activated sludge? Well, if we have an industry that has a high organic loading, and as a municipality, we've told the industry, look, we can't take that high organic loading anymore, then a high rate activated sludge process would be one way that the industry could treat their wastewater, do a pretty good job of BOD removal, maybe 70 or 80%, and reduce the BOD from 500 or 600 milligrams per liter, maybe down to 150 milligrams per liter, and send it on to the city. And that would make the city real happy. And that would be an ideal solution for the industry, because this is a very cost-effective process. We keep the reactor small, and it's, again, the most inexpensive activated sludge process you can build. But again, it has low BOD removal efficiency. We basically operate in the log growth phase or exponential growth phase. The biomass are reproducing very quickly because there's plenty of organic matter in the system. The only problem is we get very poor bioflocculation in the biomass. The bacteria, they actually secrete biopolymers that allow activated sludge to flock together and produce its good flocculent characteristics and settling characteristics. Well, in this case, with maybe a 1 to 2 day sludge age, the sludge is very young. We don't get good secretion of these natural biopolymers, and we get a flock that doesn't really settle well. It's a dispersed flock, and we're going to have trouble consistently meeting secondary treatment standards of 30 milligrams per liter BOD and TSS. Short hydraulic detention time, which keeps the reactor small, again, which keeps the cost of the facility down. Operate at a relatively low mixed liquor suspended solids concentration, very short sludge age or SRT. fairly high food to microorganism loading, very high volumetric organic loading rate, fairly high recycle ratio to keep the suspended solids in the reactor where we want it. And again, because the biomass is very young, it's not well oxidized, so the volatile fraction of the MLSS or the MLVSS to MLSS ratio will probably be about 85 and maybe as high as 90%. And going back to what I explained in previous presentations, the incoming BOD load, when it enters the activated sludge process, it's channeled in two directions. Some of it's channeled into the synthesis reaction for growing biomass. The other is channeled into the energy reaction, converting the organic matter to CO2 and water and other gaseous end products. And that's what consumes oxygen. So we're in this particular process, high rate activated sludge, most of the incoming BOD load gets channeled into the synthesis or growth reaction. We're going to produce a lot of waste activated sludge. Conventional activated sludge, again, been around for about 100 years, developed in England and Massachusetts in the US around 1910. So it's been around over 100 years, and again, a very good process for achieving biological wastewater treatment. But conventional activated sludge, we normally operate at a moderate organic loading, and we operate at a moderate sludge age. We get really our best settling activated sludge and produce a very good quality effluent. So let's talk a little bit about the characteristics of conventional activated sludge. Again, we'll get 85 to 95% BOD removal efficiency. That's excellent. We'll consistently meet 30 BOD and 30 suspended solids unless something unusual is happening. We get good bioflocculation, and we're operating in the declining or stationary growth phase of the growth curve that we talked about in the presentation on microorganisms. And the detention time in the aeration tank, generally about 4 to 8 hours. Mixed liquor suspended solids generally be somewhere around 2,000, 2,500 milligrams per liter, operate at a sludge age of about 5 to 15 days, an FO volume ratio of 0.2 to 0.6, and a volumetric organic loading rate, which is an important design parameter, typically 20 to 60 pounds of BOD per day per 1,000 cubic feet of reactor volume. And our return activated sludge rate will be about 25% to 75% of the raw wastewater flow rate. And now, since we're operating at a more moderate or medium sludge age, the biomass is a little more oxidized. The MLVSS to MLSS ratio will be about 75 to 90%. And so with conventional activated sludge, we're channeling the BOD load fairly evenly between the synthesis reaction and the energy reaction. So we'll produce a moderate amount of waste activated sludge, and we'll have a moderate oxygen demand in the process. Probably the most common type of conventional process is the plug flow activated sludge process. And here we either have a long, narrow biological reactor, or we have one shown here. It's a folded reactor, and using baffles in the reactor, we basically divide the reactor into 4 zones there, and that allows us to achieve a serpentine flow pattern and allows us to achieve a plug flow mixing regime. This is the most efficient type of activated sludge process because the wastewater stays in the reactor pretty close to the theoretical detention time. And so we have minimal short circuiting, and again, our most efficient type of activated sludge reactor. Again, we'll get about 85 to 95% BOD removal, so we'll produce a good quality effluent. Moderate aeration time, 4 to 8 or 4 to 12 hours. Return sludge flow rate about 25 to 75%. And then if we use plug flow, usually we'll keep the volumetric organic loading rate in the range of 20 to 40 pounds of BOD per day per 1,000 cubic feet. And again, we should produce a very high quality effluent. in terms of BOD and suspended solid removal. The main problem with plug flow is that if we get a shock organic load hitting at the front end of the reactor, it may upset the process. The DO may go to 0 in the front end if we get a shock organic load. And then we have an uneven O2 uptake rate along the length of the reactor, very high oxygen uptake rate at the front of the reactor and very low oxygen uptake rate at the end of the reactor. So usually what we have is that our DO may be very low at the front end of the reactor, and it may be 3 or 4 or 5 milligrams per liter at the end of the reactor. So it has some drawbacks, and but again, it's the most efficient type of reactor we have. And the main reason is that the wastewater does not short circuit the reactor. It stays in there pretty close to the hypothetical detention time. Now, one thing we can do with the plug flow reactor is we can actually taper our oxygen supply to better meet the actual oxygen requirements along the length of the reactor. So what we'll do is we'll supply more air at the front of the reactor, less at the middle, and even less at the end of the reactor. That's called tapered aeration. And that way we kind of match oxygen supply with our oxygen demand along the length of the reactor. The step feed activated sludge process is used occasionally, and it's probably the most flexible type of activated sludge process we can use. And in the typical step feed configuration, you see the reactor again. We've got a plug flow regime, but what we're doing is we're distributing the influent at 4 different locations along the length of the reactor. The first fourth will be put in right here. The second fourth of the influent loading here. The third fourth of the component of the influent loading here. And then the final 1/4 of the loading here. That's one way to do it. So what we're doing, we're again adding the organic loading along the length of the reactor. And this again helps even out the organic loading, helps us almost approximate the complete mix activated sludge process. But again, it's a very flexible type of reactor and process so that we have an opportunity to actually operate in different modes by the way when we manipulate the influent loading. Normally, SRT will be about 5 to 15 days. We'll have about a 4, 5, 6 hour hydraulic detention time. Around 3,000 milligrams per liter mixed liquor suspended solids, F/M ratio 0.2 to 0.4, and we can operate at a slightly higher organic loading, 40 to 60 pounds of BOD per day per 1,000 cubic feet. As I said before, it evens out the oxygen demand somewhat by distributing it along the length of the reactor. And again, it's a very flexible process. If we add all the influent at the front of the reactor, then we're operating in the plug flow regime. If we add all of the influent to the last portion of the reactor, then basically we're operating in the contact stabilization mode, which we'll talk about in a moment. And you might say, why would we do that? Why would we put all of the influent at the in the final compartment of a step feed system? Well, let's say if we get a real high rainfall event, we get a lot of flow coming into the process. If we operate normally, we may wash out our biomass to the final clarifier. And by adding the flow to the last compartment, then we'll reduce the likelihood that we'll get solids washout. So again, a lot of flexibility. We can carry a higher solids inventory, and then we can operate at a slightly higher VOLR, volumetric organic loading rate. So it's the most flexible type of activated sludge process we can use. So again, some of the comments I just made are stated here. The opportunity to operate in plug flow or contact stabilization mode, and then being able to handle wet weather events without washing our biomass out. One problem, if we do put all of the influent in the last compartment, we risk the problem of short circuiting and poor hydrolysis of particular organic matter that's coming in the raw wastewater. The complete mix activated sludge process was developed in the 1950s. Back in the 1950s, we didn't know what pretreatment was. We didn't regulate our industries very well. And industries would discharge high organic loadings, sometimes toxic organic loadings that completely disrupted the process. So the complete mix process was developed to help deal with that, to handle shock loadings into the activated sludge process. And the way it does that is by we will bring the influent in at multiple inlet points, and then we take the effluent from the reactor at multiple points. And that's about the only way we can achieve a completely mixed process. So we have multiple inlet points, multiple exit points of the mixed liquor. And by doing that, we can keep conditions throughout the reactor uniform. Mixed liquor suspended solids is uniform throughout the reactor. The specific oxygen uptake rate, uniform throughout the reactor. And so conditions throughout the reactor are uniform. And again, if we're hit with a shock load, it will be distributed throughout the reactor almost immediately. See some of the design parameters. Again, most of these parameters fall within what we consider conventional activated sludge, with the exception of the last one, the organic loading. And sometimes we'll operate the complete mix activated sludge process at a fairly high organic loading rate. But we have to be careful, because with the complete mix activated sludge, we have a tendency to have short circuiting. The liquid doesn't stay in the process necessarily, may stay in the process for a matter of 15 or 20 minutes, some of it is. So we have short circuiting, and that may cause us to do a poor job of removal. And complete mix activated sludge process is more susceptible to filamentous bulking, especially if you have a lot of carbohydrates in the raw wastewater. Again, the advantages: uniform organic loading throughout the reactor, uniform conditions, O2 concentration, O2 demand, handle shock loads very well. But again, because of the short circuiting problem, it's not as efficient as a plug flow reactor. So we generally make the reactor, or may make the reactor, a little bit larger to deal with the inefficiency problem. As I mentioned, we may have a filamentous bulking problem. Contact stabilization activated sludge is a process that really is probably the most cost-effective activated sludge process we can build. And the reason for that is we have a contact reactor, and typically in the contact reactor, we'll provide a hydraulic detention time of about 30 minutes to an hour, only about a half hour to 1 hour. And then we'll come out of the contact reactor and go right into the clarifier. So you might say, my goodness, how can this work with only a half hour to 1 hour hydraulic detention time in the contact tank? And the way it works is again, probably 50 to 60% of the organic material coming in the raw wastewater will be in particulate form. So in the contact reactor, in a period of 30 or 45 minutes, we can remove most of the soluble BOD, and the particulate BOD will be adsorbed into the biological flock. And so we get rid of the soluble BOD, and the particulate BOD has been adsorbed in the flock. We go to the clarifier, we remove most of the soluble BOD, and the particulate BOD is hung up in the flock, and it settles into the bottom of the clarifier. And so we still produce a fairly good quality effluent. And then we return the activated sludge, which has all that adsorbed particulate organic matter. And then in the re-aeration reactor, we'll design it to have a hydraulic detention time of about 6 times what the contact reactor has. So if we design the contact tank with about a 45-minute detention time, then the detention time in our re-aeration reactor will be about 4.5 hours. And in the re-aeration reactor here, that particulate organic matter is hydrolyzed, broken down by extracellular polymers, those are extracellular enzymes, those enzymes on the outside of the bacterial cell wall. and it'll break down that particular organic matter. It'll dissolve, be diffused across the cell wall, and be used for food. So again, that takes longer. But if you do the math with only a 45-minute detention time in the contact reactor, that reactor is very small. And then even though you designed the re-aeration reactor for maybe a 4 or 5 hour hydraulic detention time, now you're only designing it for the return activated sludge flow rate, which may be only 30 or 35 or 40% of the raw wastewater flow rate. So the total reactor volume is significantly reduced. So that greatly reduces the cost of the process. And again, very cost-effective activated sludge process. Some of the design parameters that we use, again, basically is operated in the conventional mode: moderate sludge age, 5 to 15 days, moderate F/M ratio, 0.2 to 0.6. But the organic loading may be a little bit on the high side at 60 to 75 pounds per day per 1,000 cubic feet of reactor volume. So again, very efficient removal of soluble BOD in the contact tank. The particulate organic matter is adsorbed in the contact tank, carried into the re-aeration or stabilization tank, and that's where degradation of the particulate organic matter occurs. And then we send the return sludge after degradation in the stabilization tank back to mix with the influent going into the contact tank. If you're trying to achieve nitrification, this is not a process you want to use. And it is susceptible to hydraulic shock loading, because with only a 45-minute detention time in the contact tank, you may have an issue with stormwater periods and high flows coming into the process. Give an example: the city of Memphis, when they built their 2 large wastewater treatment plants back in the mid-1970s, initially both of those plants, one designed for 90 million gallons a day average daily flow, and the other one designed for about 135 million gallons a day average daily flow. They were both initially designed as contact stabilization activated sludge. And the reason is because it kept the capital cost down to a very reasonable level in what was a very large hydraulic design. So there you have, again, an introduction to some of the activated sludge processes that we use. We'll get into more types of activated sludge process modes in the next presentation, but at least now we presented the conventional processes, and you should be somewhat familiar with them now. If you have questions, feel free to contact me at the given email address, or if you have comments about the presentation, send those to Tom Winning at Oak Ridge National Labs. Again, thank you for participating today. Hope that was beneficial to you, and hope that allows you to be more familiar with the more conventional types of activated sludge processes that we use. Thank you, and have a great day.